continue with the discussion on control hazards. So, if you recall what we were discussing in our last lecture, we looked at various schemes with which we are trying to reduce the branch penalty. But what were our approaches? We were either making some predictions, static predictions, we are assuming beforehand branch is taken or not taken, or we are relying on the compiler to move codes around and give the pipeline a better code to execute, which will generate less number of stalls. But both these approaches are static in some respect, which means whatever we are deciding or predicting or assuming, that is statically done once. Now, we look at some approaches where we try to exploit the dynamic behavior of a loop of a branch instruction to improve or enhance the performance of with respect to the control hazards even more. So, we start with this lecture. So, what I have just now mentioned, this is stated here. So, in our earlier lectures we have seen that in order to reduce the branch penalties, we are using some kind of static approach. Either you are doing some prediction, as I said, we are assuming that the branch is taken or the branch is not taken, or we are relying on the compiler, asking the compiler that, well, we have our branch delay slots, please try and fill up the branch delay slots with some useful instructions. But what we will be doing now is that these are purely hardware based approaches, what we are discussing now, to dynamically predict the outcome of a branch. Because it is dynamic, so the prediction can change with time. Like you see in a program, whenever there is a branch, depending on the program, some of the branches can be taken most of the time, some other branches can be not taken most of the time. So, you really cannot say statically beforehand that all branches are mostly taken or mostly not taken, you cannot say like that. Depending on your program, the way you have written the program, a branch can be either mostly taken or mostly not taken, or it can be 50-50 also, there can be situations. Okay? All right. So, the first approach we talk about, this uses a data structure means a hardware data structure called a branch prediction buffer. Branch prediction buffer is depicted here. So, what this BPB is? It is a small high speed memory, it is like a cache memory, a high speed memory, and this is the address of the branch which is shown in pink, okay, this one. Now, you recall in MIPS 32, whenever you have a branch address, because every instruction starts with an address which is a multiple of 4, what does that mean? That whenever you have a 32-bit address, the last 2 bits will always be 0, right? This means multiple of 4. Then you have remaining 30 bits. Here you are selecting a few bits from the lower side, let us say k number of bits. So, how many bits? That is a design parameter. This can be 4, 5, 6, whatever, let us say we use 6 bits, let us say. So, our approach will be something like this. These k bits of the branch address we are using to access this table BPB. BPB is like a small high speed memory that is indexed by the lower few bits of the instruction. What is the meaning of this? See, let us come back to this again. If I take it is 6, 2 to the power 6 means how much? 64, right. So, I will be having a small memory with 64 entries, 0, 1 up to 63. So, these few bits will be used as the address to access this memory. Okay? This is what I am saying. So, these k bits are indexed, this BPB is indexed by these k bits, and what is stored in this memory? Here the predicted branch address is stored. The predicted branch address can be either the address of the next instruction or the address of the target. Like suppose I have an instruction branch if equal to 0, let us say R1 L. So, when this instruction is executed, if it is not taken branch, so next instruction executed will be the next one. If it is a taken branch, next instruction executed will be the one from the label L. So, this is one possible branch address, this is the other possible branch address. So, the predicted branch address is stored here. Okay. So, the idea is that you check the last few k bits, you index it, look up this table and see what is stored here, and whatever is stored here, that is your predicted branch address from where you start fetching the next instruction. And this green one, you have some additional bits stored. In the 1 bit prediction scheme, you have single bits with every entry. This will tell whether the last prediction was a taken branch or a not taken branch. Let us say 0 means taken and 1 means not taken. So, that will also contain that what was the prediction, taken or not taken. Okay. So, this is how it is done. Now, in this 1 bit prediction scheme, you see just one thing. So, whenever you encounter a branch instruction, you check these k bits, go to the index and also check the prediction, because you will also come to know later whether the branch is actually taken or not taken. So, you can compare with the prediction whether this is matching, whatever was there, whether it is the same. So, if it is matching, then you know that well you are correct. But there are some problems. This 1 bit prediction scheme means the prediction may be incorrect because the value you are getting from the BPB, it may correspond to some other branch instruction also that has the same low order k address bits. Like here you are using a particular branch address, right, you are looking at the last k bits. So, there can be some other branch address for which accidentally these k bits may be identical. So, they will both point to the same location. So, you will be trying to get the same entry here in the BPB and say that this will be your target branch address. Obviously, maybe this entry was for this one. Now, by mistake for the other one also you are mapped here. So, that will be a wrong prediction. Okay. So, sometimes the prediction may be incorrect, and here the instruction fetching will begin from the predicted address, and during execution later on, well, for MIPS 32 as I said, at the end of ID you will come to know whether your prediction is right or wrong. So, at the end of ID anyway you will be knowing that whatever you have taken from BPB and you are going ahead was a right prediction or a wrong prediction. So, if you later on see that your prediction is wrong, you can appropriately change the prediction bit in the BPB, because as I said there is a prediction bit in the BPB which will tell whether the last prediction was taken or not taken. Okay. And instruction fetching will begin from the predicted address. Now, the drawback here is that suppose I have a branch instruction which is taken most of the time. So, when it is not taken, there will be 2 incorrect predictions rather than 1. Why? Let us look at a scenario. Suppose I have a loop let us say the loop is executing 100 times. So, for 99 of the time it will be branch yes, taken branch, but for the last time it will be coming out of the loop, that will be a wrong prediction. So, this out of this 100, the last time you will be getting one wrong prediction. So, that bit will be appropriately inverted also in BPB, that it is a not taken. For the earlier 99 times it was taken. So, in BPB that entry was showing as taken. Next time when you again go back and enter that loop again, maybe this is a nested loop. Next time when you enter that loop again, the first iteration of that loop there will again be a misprediction, because last time you had set the prediction bit to not taken because it has come out of the loop. But next time when you enter, the first time there will be a loop again, so there will be a wrong prediction. So, there will be twice last iteration of last iteration of the current loop and the first iteration of the next loop. There will be two mispredictions for every execution of the loop. Okay. So, let us take an example. So, here I have a loop, whatever I am trying to explain. Let us say I have a loop here, inner loop, that executes 20 times, okay, and this is inside an outer loop. So, I am looking at the inner loop. So, inner loop is executing 20 times. So, what we are saying that for this inner loop there will be two mispredictions, last iteration of the current loop. So, when I equal to 19, last time it will be coming out of the loop, but for I equal to 0 to 18 it was looping taken, but for I equal to 19 it will be not taken. But when it comes back and enters the loop again for the next loop of the outer loop, next iteration of the outer loop, so again it will start with I equal to 0, and last time it was a not taken prediction. So, with not taken for I equal to 0, it will try to take the branch, so it will be a misprediction again. So, the first iteration of the next loop will also be a misprediction. So, actually though this branch is taken 95% of the time, in reality 19 times it is taken, one time it is not taken, but this one bit prediction scheme provides correct prediction 18 times and twice it is mispredicting. So, it is having 90% accuracy, right. This is one drawback of this one bit prediction scheme. So, to avoid it, you can have a 2-bit prediction scheme, because the trouble with the earlier scheme was that every time there was a misprediction, I was flipping that bit, like in that branch prediction buffer BPB, there was this prediction bit, this was 0 or 1, 0 means let us say taken, 1 means let us say not taken. So, here we were flipping this bit as soon as there is a misprediction. Okay, we are not taking this fact into account, just like the early example showed, that most of the practical scenarios will be like this, and if you follow this immediately flipping policy, there will be two mispredictions in every loop. So, our modified strategy will go like this. We are saying that, well, let us do like this, we will not change the prediction every time there is a misprediction, we will be waiting 2 times. If there is 2 consecutive mispredictions, then only we will be changing the prediction information. Okay. If we do it, then if you think of the earlier case, then 19 of the times we can have correct prediction. Let us see how it works. Here we try to avoid the 2 mispredictions per loop in the example that I have shown for the 1 bit prediction scheme. Let us see. Here in the 2 bit scheme, I am showing a state transition diagram. The green states, these are the states, 4 states are shown. the green states are the stable states. 0 0 indicates predict not taken, 1 1 indicates predict taken. So, while you are here, if your loop you are saying taken taken taken, you remain here, and while you are here, if it is not taken not taken not taken, you remain here. But if it is predict taken, if you get a not taken misprediction, you do not straight away go here, but rather you come to an intermediate state. This is still predict taken, but maybe. So, here if you see that next time again there is a misprediction, then only you move here, which means that your behavior of the loop has possibly changed. Earlier it was mostly taken, now somehow it has become mostly not taken. Okay. But if you see that the next time it is again taken, you again come back here. Similar is the case here. If it is not taken and if you find it is a taken a misprediction, you temporarily come here. This is again predict not taken, but not green maybe case. So, if it is again a taken, that means 2 consecutive mispredictions, then you permanently move here, and if it is again a not taken, you again come back here. Okay. So, since each state is encoded in 2 bits, we call it a 2-bit prediction scheme. So, here your prediction is changing only after 2 consecutive mispredictions. So, in general this will give you better behavior as compared to the 1-bit prediction scheme. Now, the thing is that for a MIPS 32 pipeline, really you do not gain much with this, because in MIPS 32 pipeline, as I said, because of the simplicity of the instruction set, simplicity of the instruction encoding, we will come to know everything at the end of ID anyway. We will know whether the branch will be taken or not taken. We will also know the address of the target at the end of ID itself. So, whether you are using 1-bit prediction or 2-bit prediction, it really does not help much in for MIPS 32, because we have to wait till the end of ID to come to know that whether our prediction was correct or not correct, right. This is what I told. So, for MIPS 32 pipeline, we need to do something more. See, if we look at the pipeline stages again, it was fetch, it was decode, it was execute, mem and WB. Suppose this is a branch instruction, okay. This was executing. What I am saying is that it is only at the end of ID here you come to know about the branch outcome precisely. So, all your decision will be here, but because you will be fetching the next instruction immediately here, but branch outcome is known later. So, maybe this fetching will be wrong. So, what we are trying to do here is that, can we do something in the IF stage itself, so that fetching can start in the immediately next cycle with some predictive accuracy, because this is a branch instruction we cannot know until ID is over anyway. Okay? This is the trouble, but here we are saying that, well, we do not know this is a branch, all right. You see, there are 2 things. Firstly, I am saying that the instruction, unless you decode it during the ID stage, you will not know that it is a branch instruction, and if you do not know it is a branch instruction, then all these things become meaningless. It can be an add instruction also. But what you can do better is that you apply a little intelligence. Suppose I maintain the address, memory address of the instructions. I know that the instruction at memory address 1000 is a branch. So, whenever I am fetching an instruction, I am comparing that the value of the program counter from where I am fetching is that the address of a known branch instruction which I had seen earlier. There will be another table, I compare. If I see that 1000 is there, so I will know that well I am fetching, I do not know what instruction it is, but because 1000 is there in that table, I will know that this is a branch instruction. Because of that, this 1000 is in that table. So, I can start my manipulation during IF itself, I will not have to wait till ID. Okay. So, this is the philosophy we will be following now. So, this last statement actually talks about that to improve the MIPS 32 performance, we need to know from what address to fetch by the end of IF. Whether the instruction is a branch, as I said, it is not decoded yet, decoding will be done only during ID. And what is the predicted next value of PC, this also we want. Okay, we want so many things earlier before the instruction is decoded. So, we use something called branch target buffer. BTB is a high speed memory. Let us look into this into some detail to explain how it works. So, it is a high speed memory, just like the earlier data structure we saw, the branch prediction buffer that stores the predicted address for the next instruction after a branch. So, whenever there is a branch instruction, from where you will be fetching the next instruction? Is it the next instruction following, or is it the target instruction? That will be your predicted next instruction. Okay? That will be stored there. Since we are predicting the next instruction from where we are fetching before the decoding, because we will also have to know whether the fetched instruction is predicted as taken branch or not. So, we will see this structure, data structure, how it is there. So, just as I said, the program counter, the PC value from where you are fetching the instruction, that also needs to be stored in that memory, because that will tell me whether that is a known address of a branch instruction. Like I will come back to this, let me show a diagram first. You see, this is how the table looks like. There are actually three parts. The first part is the address of the branch instruction, this is the PC value. Then the predicted next address. So, while you are fetching an instruction, this is actually an associative memory, you will have to search this parallelly. So, when an instruction is being fetched, you parallelly check whether this PC value is already present here or not. If we see that it is already present, what it means? It means that the instruction is a branch instruction, because only the addresses of the branch instructions will be storing in this table. So, if the PC is matching here, you will definitely know that this is a branch instruction, and if it is a branch instruction, then the corresponding predicted PC value, that you will be using as your next PC from here to fetch the instruction. But if you see that it is not matching, then it is not predicted as a branch, you proceed normally. And also there is a third field, taken or not taken. So, you also keep this, so that if there is a prediction mismatch, you can update this. Okay. Let us go back. So, the PC of the instruction being fetched is matched against a set of instruction addresses stored in the table. As I said, these table, whatever is stored there, they represent addresses of known branches that were encountered earlier, and it also stores whether the branch was predicted as taken or not taken. Okay. So, this is the data structure and this is how you are comparing. So, how we will be using it now, let us see. This is the flow chart which tells you what happens during the IF stage, what happens during ID, what happens during EX. Now, during the IF stage, as you can see, you are sending the program counter to memory for fetching the instruction. Parallelly, you are also sending it to BTB, just like here. You are also sending the PC to BTB for searching here. So, while it is being fetched, you parallelly check whether it is in the branch target buffer or not. Suppose you find yes, which means it is a branch instruction, you send out the predicted PC, where from here predicted PC. Well, at the end of the ID, the instruction which was fetched will also have completed the decoding process. So, then you also know whether your prediction and the decoding of the instruction, whatever was there, the prediction is matching or not. If you see that the predictions match, which means whatever you are doing, whatever the predicted PC value you are using, that is the correct prediction, you continue execution without any stalls. But if you see that, well, prediction is wrong because your table says that it is taken, but after decoding you see that it is not taken, that means it is a mispredicted branch. So, if it is a mispredicted branch, then you will have to kill the instruction you have fetched. So, you need a stall here and you will have to restart fetch at the other target. And once you do this, you will also have to update BTB because now your prediction has changed. So, you will have to modify this T and NT and also update the predicted PC. Okay. And here, if it is not in the BTB, well, it can mean two things, that it is either not a branch instruction or it is a branch instruction, but you are seeing it for the first time. So, whether or not it is a branch instruction, that again you will come to know during ID. If you see that it is a branch instruction, then you will have to enter this information into BTB because you are seeing the branch instruction for the first time. But if it is not, it is a non-branch instruction, you proceed normally to the execution cycle EX. This is how it works. Okay. Now, this table shows the various penalties. You see, if an entry is found in the BTB and the prediction is correct, prediction is true and the actual branch was true, then there is no penalty, or it is not taken and not taken, then also there is no penalty. But if the prediction is wrong, found in the BTB, prediction is true, actual branch is taken, not taken, or it is not taken and taken, then the penalty cycles can be 2. Why 2? Well, means earlier we had seen that penalty is 1 for branch, but here since we also have to update the BTB, we assume that for updating BTB we need another cycle. So, that is why the penalty we are saying as 2. Okay. And if it is not found in the BTB, you will have to update the BTB for actual branch is taken, penalty cycle is 2. If the actual branch is not taken, penalty cycle is 1. So, these are the assumed values, and there is also justification as I said. So, this is what I said, since the BTB may also need to be updated, the penalty can be 2 clock cycles in these cases, because here you have to update BTB, right. Fine. Now, there is a small example where you can work out based on these values. That let us take an example where the BTB, there is a BTB and 90% of the branches in a program, they are actually found in BTB, and out of them 8% of the predictions are incorrect and the remaining 92% are correct, and 75% of the branches are actually taken. So, what will be the branch penalty? So, the branch penalty will be, just you follow in the table, wherever there is penalty 2, 2, 2, 1, these are the 4 cases where there is penalty, right. The first case is branch found in BTB and there is misprediction. For this penalty is 2, you see there is a 2 here and a 2 here, found in the buffer, but there is a misprediction. Or not found in BTB and is taken branch, for this it is 2, this is 2. Not found in BTB, not taken branch, for this it is 1, this is 1. Okay. Now, just put the values, percentage branch is 0.9, misprediction is 0.08, not found in BTB is 10%, 75% taken branch, 25% not taken branch. So, if we calculate, branch penalty comes to 0.32 clock cycles. So, you compare this with delayed branches where the average penalty was 0.5 clock cycles, but here based on the realistic values on real programs, you see that your performance can become better, your branch penalty becomes less than 0.5. Okay. And lastly, you will look at some conditional instructions which also help in reducing branch penalties. In fact, MIPS has a number of such conditional instructions. So, what are conditional instructions? There is something like conditional moves. Let us look at a justification why you need this. Consider a C code like this: if x equal to 0, a equal to b. This is a conditional move. Okay. Let us say register R1 holds the address of x, R2 holds the address of a, R3 holds the address of b. Not the address, the values of ABC, let us say values. So, just using conventional branch instruction, our program will be like this: branch if not 0, R1, you skip, if it is 0, then only you move R3 to R2, add R3 and 0, move it to R2, a equal to b. But there is a conditional move instruction also in MIPS. It says conditional move if 0, R2, R3, R1. It says if R1 is 0, then move R3 to R2. So, you can avoid the branch instruction altogether. So, whatever control hazards were there, you are avoiding this. So, basically we are converting the control dependency into data dependency. So, MIPS in fact has a whole set of conditional instructions just for this purpose. The compiler can use it to advantage and eliminate many branch instructions. So, with this we come to the end of this lecture, and over the last few lectures we discussed the various hazard scenarios in the MIPS pipeline, and we had looked at many of the modern techniques that are used to detect and mitigate the effects of hazards. So, we shall see some other advanced issues later in some lectures, but for this lecture I think we are done and we can stop here. Thank you.